Good afternoon, students. In this lecture, we are going to see the topic of properties of gases and gas mixtures. In order to see the topic of gas mixtures, first we should understand what are the properties of gases. Then we go to the point of properties of gas mixtures. So, this part of the syllabus, the blue color one, is given in your syllabus. The same thing I have reframed into this manner so that you will know the each topic here. So we will be seeing this in this manner. So we'll be interested in looking at the properties of gases now. So in properties of gases, the basic and most important law is Avogadro law. So what does this Avogadro law say? This Avogadro law basically states that a mole of a substance, a mole of a substance has a mass numerically equal to the molecular weight of the substance. The molecular weight of the substance. So what does this law say? You will take a mole of a substance, and that mole of a given substance is numerically equal to the molecular weight of a substance. So in order to understand this, first let us take the example of oxygen. If you take oxygen, this oxygen, let's say you have taken 1 kg mole of it. So 1 kg mole of oxygen, 1 kg mole of oxygen will take 32 kg of mass. So what is the meaning of this? If I look at this here, N is the number of moles, that is your kg moles, that is equal to, I think I should write this quite bit clearly, this is not clear here, 1 kg mole. Okay, so the N, if I take, this number of moles is equal to mass by molecular weight. So when I take M here, M is nothing but the mass of substance measured in kgs, and MW is nothing but the molecular weight of the substance. And the molecular weight, it has kg per kg mole as a unit. So since in the numerator you have kg and in the denominator you have kg per kg mole, here this kg gets cancelled and you will have kg mole as the unit of your N. So N is the number of moles which is measured in kg moles, kg mol. I should write it clearly, kg mol. So that is N here. So how does this relate to your oxygen, that is 1 kg mole of oxygen has 32 kg of mass. Here I have missed writing kg, I will just include that kg here, 32 kg of mass. So here if I look at this particular expression, this has N in this. So this kg mole is nothing but your N, and This 32 kg is nothing but your mass. Okay. So if this is the thing, let me put this expression in a different form like this. That is, the molecular weight is equal to m by n. So here the mass given to us is 32 and n here is 1. So that will obviously give me 32. This 32 is nothing but kg per kg mole. Kg per kg mole. So the molecular weight of the oxygen is 32 kg per kg mole. Okay. So how did I get this molecular weight of the oxygen as 32 kg per kg mole? So basically, how did I get that 32 as a molecular weight of the oxygen? This is how I got it. Because the mass is 32 and the number of moles will be 1. As the mass changes, number of moles will change. Whereas a molecular weight is going to be the constant for any given substance. Similarly, if we take the nitrogen, 1 kg mole, 1 kg mole of nitrogen will have 28 kg of mass. Why? It is again based on its molecular weight. That is, if I take the molecular weight here, the formula is m by n. The m value you got as 28 here in the problem, and then n value is 1, so that will be giving you 28 here. So the molecular weight of nitrogen will be equal to, the molecular weight of the nitrogen will be equal to 28 kg per kg mole. So this will be the molecular weight formula for the nitrogen, or the molecular weight value for the nitrogen. Similarly, you can repeat it for CO2, that is carbon dioxide. If I take it for carbon dioxide, 1 kg mole of CO2, CO2 will have will have 44 kg of mass. So how can I say this? This is again based on molecular weight of the carbon dioxide. So how I can prove it? The molecular weight is equal to m by n. This is the formula we know, and we got the value of mass as 44 kg here. This is your m value, and the n value here is 1 kg. So I can write that m by n is nothing but 44 by 1, which is nothing but 44. So what I got here is the molecular weight of CO2, sorry, there is some issue. CO2 will be equal to 44 kg per kg mole. So that will be the molecular weight formula for CO2. I should not say formula actually, that should be value, the molecular weight. So based on this, we understand the concept of moles here. So that is one aspect of your Avogadro law. And one more aspect, on the most important aspect of the Avogadro law is this. For all gases, I can say this according to my Avogadro law. I repeat, this is for all gases, for all gases. What I can say is, let me say I'm taking the N value as 1 kg mole, 1 kg mole, and I'm taking the pressure to be 1 atmosphere, that is 1.01325 bar, and the temperature to be 0 degrees centigrade, which is nothing but my 273 Kelvin. So if I take this pressure and temperature here, this pressure and temperature put together are called as normal temperature and pressure. So the atmospheric pressure and 0 degree centigrade are together called as normal temperature and pressure with the regular way of nomenclature. So at the normal temperature and pressure, 1 kg mole of a given substance for any given gas, it is valid. Okay, for any given gas, you can say that it will occupy a volume of 22.4 meter cube of volume. So this is another aspect of here Avogadro law. What it says, at the normal temperature and pressure conditions, for 1 kg mole of a given mass, it will definitely take a volume of 22.4 meter cube. So that's the thing here. So what it gives rise to is, it gives rise to something called as universal gas constant, which is represented by R bar. So the R bar is nothing but your universal gas constant. So based on your ideal gas equation, PV is equal to N R bar T. So if I write it like this, here if I want the value of R bar, that will be equal to PV by R bar T, which is equal to the pressure value. Here I can take it as the P value is nothing but your 1.01325 bar can be written as 1.01325 into 10 square kilopascal. So this P value can be substituted here directly. So this is a P value I have here, and I'm substituting the same here directly. 1.01325 into 10 square, because I want the final answer to be in kilojoules. I'm taking it in kilopascals here, and the volume, we said that the value is 22.4. So the volume value is 22.4 and the pressure value is 1.01325 bar converted into kilopascal. This is the value, and now I will have to substitute. Sorry, this should be N here. I have written a mistake here. So this should be N here. R bar is already on this side, so I should write N here. The N value is nothing but 1 kg moles. I am substituting that 1 here. This is 1 into, and the temperature substituted in SI unit will be 273 Kelvin. So 273 Kelvin. So I've substituted all the values appropriately here, so that I'll be getting the R bar value as 8.314. So this is the value I got for the R bar. So what is the unit of this R bar? We have to understand here. So if I look at this here, for pressure, the unit is kilopascal. Kilopascal is the unit of pressure, and the unit of volume is meter cube. And in the denominator, I have kg mole for N. For number of moles, it is N, and the 273 is Kelvin. So this will give rise to something called as kilojoules. How do I get the kilojoules? Here in kilopascals, I have basically kilonewton per meter square, and here I have meter cube. So this meter square and cube gets cancelled, so that what I'll get here is, in the numerator, kilojoules, which is kilonewton per meter is nothing but kilojoule, and in the denominator I'll have kg mole Kelvin. So in the numerator I have kilojoule, and in the denominator I have kg mole Kelvin. I will write it here directly for the want of space. So this will be kilojoule per kg mole Kelvin. This is the formula, I should not say formula, this is the value of your universal gas constant. Okay, this is the value of your universal gas constant. This must be by hearted and remember. And this side, what I have written is a simple conversion of the units, simple representation of the units here. I'll just complete this units also here. Kg mole Kelvin. Actually, I have kg mole Kelvin here. The same thing I have written here. So hope that is clear regarding the R bar. So with this we understand what is the universal gas constant, and it is same for all the gases, because according to your Avogadro's law, you will always have this much of volume here. The volume is 22.4. This is a very key number that you will use in the properties of gases and the mixture of gases. So 22.4 meter cube of volume for any gas at the normal temperature and pressure values per 1 kg mole of the substance. So this is the key, and with this we get something called as universal gas constants, R bar, which is 8.314 kilojoule per kg mole Kelvin, right? So now we will go to the next concept, that is specific volume. Next concept that we should learn in the properties of gases here is the specific volume. Basically, the specific volume is known to most of you by this time in the thermodynamics course. Specific, this pen is making a problem. Specific volume. The specific volume is represented generally with a small v, and which is written as a actual volume per unit mass. The volume per unit mass is nothing but your specific volume, whose SI unit is meter cube per kg. Whose SI unit is meter cube per kg. Now, with reference to this, we define something called as a moral. It's not moral, it's molar. Molar. Molar volume. So this molar volume, you will represent it with V, small v with a bar on it. Small with a bar is nothing but the molar volume. It is taken as volume by N is taken here. N meaning the number of moles. So when you take the number of moles here, what you will get here is SI unit. This will be meter cube per kg mole. Meter cube per kg mole is the SI unit here for the molar volume. So this definition also must be known at this level. So here V is nothing but your total volume. V is total volume. See, V with a dash I show to represent that it is a capital V, and the small v is written like this. Okay, have that in mind. And now if you look at your PV is equal to nRT and PV is equal to MRT also, you must be learning. So here you have the forms of your ideal gas equation. Okay, so those forms you should understand. So before we go to the forms, I must tell you what is the difference between R and R bar. So let's see this first and then go to the ideal gas equation. So R and R bars. So the R bar is nothing but your universal gas constant. R bar is universal gas constant, and this value is same for all gases. This value is same for all gases, and its value is nothing but R bar equal to 8.314. This we have seen already. 8.314 kilojoule per kg mole Kelvin. Kilojoule per kg mole Kelvin is the R bar value, and it is same for all the gases. But whereas R, if you take, R is a characteristic gas constant. Characteristic gas constant, and it will vary for each gas. So how it will vary? Let us see an example of air here. If I take an example of air as my gas I am taking here. For this, the Cp value must be known to you by now. The Cp value for air is 1.005 kilojoule per kg Kelvin. Kilojoule per kg Kelvin, that's the Cp value. Specific heat at constant pressure, and Cv value is specific heat at constant volume, which is 0.717 kilojoule per kg Kelvin. Kilojoule per kg Kelvin. So now if I want the R value for air, R is nothing but Cp minus Cv. This formula also must be known to you by now. So 1.005 minus 1.005 minus 0.717. If I substitute here, it is nothing but the R value equal to 0.287, which is measured in kilojoule per kg Kelvin. This is measured in kilojoule per kg Kelvin. This is R value for air only. So if you take some other substance, this will vary. So the point here is the R value is the characteristic gas constant, which is also called as particular gas constant. Then another name is particular gas constant, because for a particular gas it will have a particular value. That's why it's called as particular gas constant also. So for air, this is an example, and you can keep on writing the examples for other gases as well. So the universal gas constant is same for all gases, and the characteristic gas constant is a particular, and it will be varying for each gas. For air, its value is 0.287, whereas the R bar is same for all the gases. Even for air, this R bar is 8.314. Okay, so if with this in background, let us look at some relationship between R and R bar. If I have to tell what is the relationship between R and R bar now, so now I can relate these two based on my molecular weight. So the R bar will be equal to the Cp minus Cv into the molecular weight. So this is how you take it for R bar, where you are getting the molecular weight into the picture here. Okay, so here the unit for Cp minus Cv is kilojoule per kg Kelvin. Let me write it here. Kilojoule per kg Kelvin into the molecular weight is kg per kg mole. So here the kg gets cancelled, and what you get ultimately out of this will be kilojoule per kg mole Kelvin. This kilojoule per kg mole Kelvin is nothing but the unit of your R bar. So it is making sense. So the formula that I have written here, R bar is equal to Cp minus Cv into molecular weight, is making sense. So that is a correct formula or a correct relationship between R bar with Cp minus Cv. So the same thing here, I can write it in the form of R as well, right? Why? Because R bar is equal to R into the molecular weight, because Cp minus Cv is nothing but your R. So this is the relationship between R bar and R. You can transform it into various forms. The R bar and R relationship is dependent on the molecular weight. So you have to appropriately multiply or divide it with the molecular weight. So you will divide it if you are writing in terms of R. The same equation you can write in terms of R is equal to R bar by the molecular weight. So this way also you can write. So you can take various other forms as well based on the requirement and the need. That is the relationship between your R and R bar. So further, we should look at the forms of ideal gas equation. So far we have discussed about the Avogadro law. If I go back to your syllabus here, So in your syllabus, we have discussed about the Avogadro law, and we have seen various aspects of Avogadro law so far. Now we will go into the ideal gas equation now. So if I take the ideal gas equation here, ideal gas equation, and this ideal gas equation can have many forms based on your R, based on your M, and so on. You can have various forms of ideal gas equation. Let us take the first form and let's call it as 1A. Form 1A, or 1A form I can say. Okay. So in this form, if I write this expression here, this is going to be like this. PV is equal to N R bar T. See, whenever I write my equation in terms of N, I should write it in terms of R bar. Okay, that's the thing here. So if I am writing it in terms of PV is equal to R bar terms, I should have N here. Okay, that is the thing here. So here, if I take P as my first thing, this P will have a unit of kilopascal. Okay, this P will have a unit of kilopascal, and the volume will have a unit of meter cube, and N will have a unit of kg mole, and the R will have a unit of kilojoule per kg mole Kelvin, and the T will have a unit of Kelvin. So this is one important form which you should understand, along with its units. PV is equal to NR bar T is taken in terms of R bar. So the same expression NR bar T, if I write here, I can take it maybe and name it as 1B here. If I have to name it as 1B form here, if I name it as 1B form, so what I will have here is the same expression will get transformed into my molar volumes now. So when I express the same thing in terms of my molar volume, in place of my volume, I should get V bar, small v bar, I should get some p is gone. So the small v bar I should get equal to, because capital V by N is nothing but my molar volume. So here I will not get any N part now. I'll directly go to R bar and T. So this is how I can write my ideal gas equation now. So this is a changed form of the similar one, that is your R bar based ideal gas equation. Okay, universal gas constant based ideal gas equation I have written here. For this I will be writing kilopascals here. I'll be writing this, since this is a molar volume, I should write meter cube per kg mole. And for my R bar, as usual, kilojoule per kg mole Kelvin. And for temperature, I have Kelvin again. So that's how you will get the forms 1A and 1B for your ideal gas equation based on R bar. So for these two expressions are written based on R bar, that is your universal gas constant. Now moving forward, if I have to write this in terms of particular gas constant, that is R. So let me call this as 2A form. If I write it in the 2A form, 2A form, here we will write it based on R and M. Sorry. My pen has issues here while writing, so you have to kindly excuse me. And it again got closed. Why I don't understand. So kindly bear with me for these technical glitches. Yeah. So based on R and M. So previously we have written this form based on R bar and N. The 1A and 1B are based on R bar and N. Now the 2A and 2B will be based on R and M. This is mass and that is number of moles. Now if I have to write it for the 2A form will be looking like PV is equal to M R T. So this is the expression that you will get here. So this is in the terms of R bar and M. So for this, if I have to write, my pen is having an issue. Excuse me for that. Fine. So this looks fine, and now this P has a unit of kilopascal as usual, and the V has a unit of meter cube, and the mass has a unit of kg, and R will be having a unit of kilojoule per kg Kelvin now, and the T will be having a unit of Kelvin now. So this is the form for your 2A. Now let us try to write it for 2B. 2B form. There are basically 4 forms that you should learn here. First 2 are based on R bar and M, and second 2 are based on R and M. So if I write it here, I should write it in the terms of specific enthalpy, specific volume now, because since V by M is nothing but your small v, that is specific volume. So in terms of that, you have to write here P V. I think I should write V more clearly. PV equal to RT. So this is one more form of the expression here, that is 2B form. So this is one more expression, and its units are kilopascal, and this unit is meter cube, and this unit is kilojoule per kg Kelvin, and the T unit is Kelvin. So these are the various forms of the ideal gas equation along with its units. Okay, so in this context, it is also important to learn some basic things. This might be covered in the other parts of thermodynamics as well, but here again it may be a repetition, but still it makes sense because they are of great use to you while solving the problems on mixture of gases. So let us look at some concepts which are useful to you for the problems in the next part. So here we should understand what is the relationship of specific heats with enthalpy and internal energy. With enthalpy and internal energy. Yeah, so this part we should understand. So if I take Cp, by definition Cp will be equal to dH by dt. So this is a relationship between your specific heat at constant pressure with enthalpy, and by definition if I write Cv, Cv will be equal to du by dt. So that is specific heat at constant volume is related with the internal energy here, that is U. Okay, so H is your enthalpy and U is your internal energy. With respect to temperature, you relate them here. So here you can write that dH is nothing but Cp dt and du is nothing but Cv dt. So these expressions of enthalpy and internal energy should be known in terms of specific heat in solving the problems that you're going to see in the future. Okay. Also, the concept of adiabatic index should be known. Adiabatic index. So what is this adiabatic index say? This adiabatic index says that the Cp by Cv ratio will be gamma, which gamma is nothing but your adiabatic index. So this value will be varying based on your gas. For example, if you take air, this gamma value is 1.4. That is the thing. And now, based on this, we should also be relating your particular gas constant here. So if you want to relate it to particular gas constant, Cp minus Cv will be equal to R. So based on this, you can have the R value written in various forms here. So the R value, if I have to write here, the R value will be equal to the Cp into 1 minus 1 by gamma. So actually I made use of this here, and the combination of this first expression and the second expression I have taken to get the third expression. Okay, same thing I can do with my Cv as well. R is equal to Cv. If I take as a common here, what I will get is I'll get gamma minus 1 as my expression here. So generally these expressions, I think I better explain this clearly here. So this I got based on this. Maybe if I write it in the other way around, it will help. So what I should do is I should better write the R here. The R is equal to Cp minus Cv. So in this R, I'll take Cp as common. If I take Cp as common, 1 will be remaining here, and I'll get Cv by Cp here, which is nothing but 1 by gamma that I have written here. And the same expression can also be written in the more famous form R equal to this I write it in the Cp itself. This is more famous comparatively. The Cp is equal to gamma R by gamma minus 1. This is nothing but your relationship between Cp and R without Cv, I must say, without Cv. This is one expression that you should learn. And similarly, if I take this R and I take CV as common here, then what I'll be getting here is I'll get Cp by Cv here, which is nothing but gamma, and I'll have 1 here. So this will give rise to a Cv expression without Cp, which is equal to R by gamma minus 1. So these expressions must be learned by you, and you can cross check all these values here for air. Let us say the gamma value for air is 1.4 and the R value for air is 0.287, that too measured in kilojoule per kg Kelvin. So if you substitute this gamma value here in this Cp expression, then here you will get that value as 1.005 kilojoule per kg Kelvin. And if you substitute this gamma value and R value here, you'll get this expression as 0.717 kilojoule per kg Kelvin. So these are all kind of transformations of the same stuff. Okay. So along with this relationship of specific heat with enthalpy and internal energy, one more concept is required to be learnt here. That concept is the concept of entropy change for ideal gas. Entropy change for ideal gas. Change for ideal gas. This is one more concept here. Okay. Before I jump into it, I should first write the expression of the first law. The first law expression is Q is equal to U plus W. This expression is very well known expression based on the first law. So here, if I write it in the differential form, dq is equal to du plus dw, I will get here. So if it is a reversible process, q is equal to tds. This is also known from the Clausius-Clapeyron equation, Clausius inequality I should say. So dq is equal to tds based on your Clausius inequality for a reversible process. Dq is equal to tds. So I can substitute that there. And in place of du, I am writing du only. Here I am writing it in the specific internal energy terms. And also I can write dw is nothing but pdv. This is a very well known formula. So TDS is equal to du plus pdv is a one form of writing your change in entropy. So ds, the change in entropy, you will write it in this form. Based on this form, you can get one more useful form for solving various problems. For getting that form, I'll just transform this expression here. I'll 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 take the t value onto the other side. ds is equal to, I will do du by t plus p by t by t into dv. This is what I will get here. So in order to transform it further, what I will do is, I know that du is equal to cv into dt. So I will substitute that here, cv into, I will write it like dt by t, so plus, and then here I have this P by T into dV, which is nothing but R by V. So how do I get that? I get that based on PV is equal to RT. So I can write it something like P by T is equal to R by V. So this when I say V here, I'm speaking about a specific volume. Okay. So I can write it like P by T is R into dV by V. Okay. So this expression if I take and if I apply the integration over both sides, if I apply the integration here and integration here and integration here, so if I apply integration, what I'll get is between two states, I'll get this is S2 minus S1 here, and here I'll be getting integral 1 by t dt is nothing but your log t. So log higher limit minus log lower limit. If I do that, log a minus log b, I will get that is nothing but log a by b. So what I will do here is I will write it as Cv into ln. I'm using natural log to the base e here. I will use ln t2 by t1 as my expression. So that's how it will get transformed to on the first part. And the second part, if I write similarly, I'll get r into ln v2 by v1. v2 by v1. So this will be my entropy change expression. This is an important expression, and this expression if you look at is in the form of Cv and R. So this one let us call it as S1 equation. Okay, this is the entropy equation, entropy change equation in its first form. Similarly, you can have it other two forms also. So in order to look at the other two forms, let us take one more example now. Here let us take the case of your enthalpy. By definition, enthalpy H is equal to U plus PV. This definition is a very well known definition, and now I will apply difference on the both sides. So dH is equal to du plus, since this is two terms here, I should apply the differentiation. uv whole dash is equal to u dash v plus v dash u. So for that, what I'm doing is I'm writing it as pdv plus vdp. So this is how I have written. So if you look at this carefully, this part is nothing but your TDS in the previous expression that we have written. So if you look at the expression 1 here, this expression 1 is nothing but du plus pdv, which is equal to TDS. So the same thing I will substitute here, and I will write this dH is equal to TDS TDS plus VDP. So basically what I want here is TDS. Okay. I want the entropy change. I will take the TDS onto this side. So this TDS will be DH minus VDP. So this is another form of your TDS expression. Okay. This expression, let's call it as 2. This expression is 1. Okay. 1 and 2 are TDS expressions, which is measured um, in terms of internal energy in 1 and in terms of enthalpy in 2. Okay, so you can use this expression now in order to get one more kind of entropy change expression here. For that, what you can do is you can take only ds on your left hand side, and you can take this t onto the right hand side, so that what you will get here is dh by t minus v by t into dp. So here this dH we know is equal to CP dt. dH is equal to CP dt, and also I know the V by T based on my ideal gas equation. This is nothing but R by P. So if I substitute that here, this ds will become something like, there is an issue again, I'm sorry for all that. So ds, I don't know what's happening here. ds is equal to the Cp dt by T. Okay, I can write this like this, and then I can write this in terms of my R by P. Actually, this should be P. R by P. So since I have dP here, I will write by dP by P. R into dP by P I will get here. This is my expression, and I will apply the integration on the three terms here, left hand side and right hand side. If I do this integration here, if I do integration here, I'll be getting S2 minus S1 expression here, which is equal to Cp into ln T2 by T1 minus R into ln P2 by P1. This is the expression that you got for your entropy change. So if you closely look at this expression is based on your Cp and R. Previously you got S1 and this will be S2. So S1 is based on your Cv and R, S2 is based on Cp and R. That's the difference. And you can also have S3 here, which will be in terms of Cp and Cv, where you will not have any R in it. Okay, so if you write that third case here, okay, for the third case, you know that R is equal to Cp minus Cv. I don't know why my pen is not working properly, but bear with me for that. This Cp minus Cv I have. What I will do, I will take the expression of S2 and in place of R I will substitute this. Substituting in S2. If I substitute this R is equal to Cp minus Cv here, so the expression will turn out to be like this: S2 minus S1 equal to the Cp into ln T2 by T1 minus, since I have Cp here, the Cp should be multiplied with my ln P2 by P1, and this minus into minus will become plus here. I will get Cv here, ln, again I have P2 by P1. So for this S2 minus S1, if I take this Cp as common for these first two terms, how I'm going to get is the Cp into ln of T2 by T1 into P1 by P2 I will get. Because there is minus here, this should be A by B. So if I do that, log A minus log B equal to log A by B, I will get reverse expression here, plus Cv into ln P2 by P1. So this expression is nothing but here V2 by V1. So how do I get that? For that purpose, what I will do is I will take, since V2 is equal to T2 by P2 into R, and V1, I best write 1 by V1. 1 by V1 equal to P1 by T1 into 1 by R. So if I take the V2 by V1, that will be equal to this R and this R getting cancelled. What I will be left with is T2 by T1 into P1 by P2. So what I can write here is, in this expression of S2 minus S1 will be equal to Cp into ln V2, I should actually write it as small v2, by V1 plus Cv into ln of P2 by P1. So if you look at this particular expression is in terms of Cp and Cv. So you can call this expression as S3 now. So in total, you got three expressions which you should remember here. The first one is your S1 equation. Let us put this S1 equation there. Let me copy this and put it here. This is my S1 expression. And now let me also copy my S2 expression. This is my S2 expression. And then I also have my S3 expression. So these are the expressions I am having here. All the three expressions. This has some copying issue. P1. So these are the expressions for your S1. This is S1 expression. This is S2 expression. And this S3 expression. You are supposed to by heart all these expressions, S1, S2 and S3. All the expressions are very important expressions for solving the problems that you will do in the next class. Okay, so with this we will close it here, and we will see the next topic, that is Dalton's law of partial pressures, in the upcoming lecture. So far, if you look at your syllabus, you have completed the first part. In the next lecture, I am going to start the Dalton's law of partial pressures. Thank you.